Hello everyone, my name is Chandan, and in this video I'm going to talk about the Contiki-OS, its installation, and some of the few features that are included in the Contiki-OS. So, what is the Contiki-OS? It is an open source operating system that runs on the tiny low power microcontrollers and makes it possible to develop applications that make efficient use of the hardware while providing standardized low power wireless communication for a range of hardware platforms. In order to download the Contiki OS, you need to go to contiki-os.org and click on the download tab. And now click on download instant Contiki and select the version of Contiki OS that you want to use. In this case, we are downloading the latest version, that is Instant Contiki 2.7. After you download the zip file, you need to extract the folder and store it in your desktop. These are the list of folders that you get in the downloaded file. Now, in order to run your Instant Contiki OS, you need to open the virtual machine installed in your computer. In case you do not have the VMware player, you can go to vmware.com to download the latest version of VMware. Now, after the VMware player opens up, you need to click on the option Open a Virtual Machine. Now go to the path where you have stored your Instant Contiki folder and click on the virtual machine configuration file. And now click on Play Virtual Machine. Now, why we are using the Contiki OS is because of three major reasons. 1. It supports a fully standardized IPv6 and IPv4 internet standards, and along with this, it also supports the recent low power wireless standards like 6LoWPAN, RPL, COAP, etc. Second, it supports the rapid development. That is, with Contiki, development is easy and fast. Contiki applications are written in standard C language and hence it is easy to code. And last, it is open source. It is an open source software which can be freely used in commercial and non-commercial systems which can run many Internet of Things applications. So, what is the Internet of Things? It is a scenario in which the objects, animals, or people are provided with unique identifiers and the ability to transfer data over a network without requiring human-to-human interaction. So, IoT has evolved from the convergence of wireless technology, the mechanical systems, and of course the Internet. There are many applications of the Internet of Things. Some of them include using the wireless sensor networks and the IoT in agriculture, and also air pollution control systems, water quality control systems, waste management systems, smart parking systems, and water leakage systems, etc. And now we are waiting for the Instant Contiki OS to boot up on the Ubuntu. Now you need to select the Instant Contiki and the default password is user. This loads up the Instant Contiki OS on your VMware player. Now, what we are going to see are the few features that are included in the Contiki OS. So, you need to go to Places, Home folder, and then click on Contiki folder. And in order to see the hardware platforms that are supported by the Contiki OS, you need to go to the Platforms folder. In this folder, you get all the list of all the hardware platforms on which the Contiki programs and applications are supported. Right now, we are considering the Sky Mode hardware. Also, in order to view the header files and the library files that can be used on your C programs that are run on the Contiki OS, you can go to the core folder and access all of these files. To check out some of the example programs, you can go to the examples folder and see the various examples that are provided in this OS. These include the collect program, which actually collects the data from the sensors and sends the data over to the gateway node. So these are just some of the few features that are included in the Contiki OS. Now, in order to update your Contiki OS to the latest version, you need to go to your terminal and click on the following commands. You need to go to the path where you have stored your Contiki OS, and then you need to type the command cvs update -dp. Executing these commands installs the latest version and the packages for your Contiki OS. Since we have downloaded the latest version, that is the Instant Contiki 2.7, we need not execute these commands in our terminal. So this was just a quick tour on how to install the Contiki OS on your machine. Now, in the next video, we are going to show you how to write the code on the Instant Contiki OS. Thank you.
Hello everyone, I'm Sudarshan here. I'm going to explain how to run hardware code in Contiki. So this is our Contiki operating system. So basically Contiki is used to compile and upload the program into a mode. There are so many types of modes available, such as Z1, Sky mode, Contiki-COOJA mode. So in this case we are not using any hardware mode, so I'm just going to explain the basic steps needed to compile and upload the program into a mode. So to compile the program, at first we have to set the target. So target can be set using this command. If you are using a COOJA mode, it will be equal to COOJA. If you are using Sky, it will be Sky. So I'm going to use Z1 mode. So program name, the program which we are going to compile. So this command will compile the program in our system. So next step is to upload the compiled program into our mode. So it can be done using this command. It's make program name dot upload. It will generate a upload file after compilation. So it will upload it to the hardware. So now we are making login in order to view the compiled code. So target is equal to Z1. It will log in into the hardware, that is Z1 mode, and it will display the output over there. So now I'm going to explain it with an example. So in this case we are using Blink program as an example. This program has two processes, that is hello world and Blink process. So in hello world process we are just displaying the count value, and in Blink process we are using LED. It is it will show the LED status. Okay. It's stored in example folder. So at first we have to make a makefile. This makefile is essential to compile a hardware program in COOJA, because makefile it links the essential files as well as the build system to our program. So in this case we are linking to Contiki 2.7 folder, and we are including the build system, that is makefile.include here. So this is the makefile content. It should be saved in same location as the program stored. Now it's time to compile the program. It's make target. Since we are not using any hardware here, we are just setting target as native. So it will compile the code and show the output on console only. So now the program name, that is blink. So it start compiling. Yeah, it finished compilation process. So here an example folder, a .native file is generated. It is nothing but compile firmware. So to view the compile firmware, I'm gonna execute the command, that is blink .native. So it will run the program, it will show the output. So here the output is, it will show the LED status at each second, and it prints the count value after 4 seconds. So it keeps printing. So I'm gonna explain the code in brief. So in blink.c, at first we are initializing two processes, that is hello world and blink process. So auto start process, it starts the processes automatically as soon as we compile the program. So hello world process starts here, it begins, and here we have e timer. So it is set to 4 seconds. So there are three types of timer in Contiki, that is e timer, c timer, and normal timer. E timer is used to generate an event at the end of the timer, and c timer is used to call a function at the end, and normal timer is used to query the time value. So it will generate an event, that is it prints the count value at each 4 seconds. So after printing we are just resetting the timer. So this is the process to handle hello world. And it is the second process, it is used for blink the LED. So in this case we are setting the timer for just 1 second, because at each second it will blink the LED and it prints the status of the LED. So here we are using LED functions, that is LED off as well as LED on. So it is used to switch off the LED, and the second one is used to switch on the LED, and it increments the blinks count and it prints the state, and the process ends here, the process end. Yeah. So in Contiki we have multiple independent platforms such as Kuja, Sky, etc. So this is how we run the hardware code in Contiki. Thank you.
This is Ganesh Prasad. Now let us discuss about the Kuja software simulator. Let's get started. Kuja is a network simulator designed for wireless sensor networks. It is an open source simulator. It is basically built in Java and is capable of executing the C and C++ programs. The simplest way to get started is to get inside its own directory. To do so, let's start with opening a terminal. In my system, the Kuja software is placed on the desktop, so it is cd desktop followed by Contiki 2.7 followed by the tools followed by Kuja, and the command to run the simulator is ant run. This might take a few seconds. That's it. To start a new simulation, go to File, New Simulation, or use the shortcut Ctrl+N. This pops up a window asking us to enter the name for the particular simulation, and here I'm going to enter demo_1. In advanced settings we have 4 different options, and it's a radio medium. Inside radio medium we have 5 different options, one of which is no radio traffic, that is there will be no disturbances between the communication of the two nodes, followed by a constant loss. Constant loss is a predefined value where between a particular communication there is certain amount of energy which is getting lost. Another one is the distance loss. This distance loss accounts for the decrease in the signal strength as the distance between the nodes increases, and there are many other options which we can explore. Next is the mode startup delay. When there are hundreds of nodes in the simulation, all the nodes cannot get started at the same time. For that, each node will be having a startup delay which can be specified in this particular option. And the random seed option. A random seed is a number which is used to generate a random number, and that random number is used to start up the particular node after a few startup delay. Now let's get started. This is how it appears once a simulation is started. We have different windows, that is the network window, simulation control window, the nodes window, the mode output window, and the timeline window. Network window is the place where we can deploy the nodes, and we can have any of the attributes for that particular nodes applied to it. Next we have the simulation control window, where we have the controlling of the particular simulation in the form of start, pause, step, and reload. The step function is used to run the simulation for a very short interval of time, and that is 0.1 millisecond. And reload, this reload option helps us to reload this particular program automatically without we having to do it manually, and the simulation begins. Notes. This notes window is used to take down any of the nodes, important nodes regarding this particular simulation, which gets saved. Next is the mode output. This mode output window is the place where we get the output results of our simulation. That is, if there is any message passing between the nodes, this is the place where we can see those messages getting passed. And if it's a base station, a particular node gets all of the messages from all other communicating nodes, and this is where we can see all those messages getting passed. Finally, it's the timeline. This timeline refers to the simulation, how the simulation proceeds with respect to time in seconds. So to start with, we have to add the modes. Modes, add modes, create new modes, and this creation of the new mode gives us with so many options of using the different sensor nodes in the physical application. We have the Kuja mode, the Msp mode, the Sky mode, and the Z1 mode. And many other options are also available. To start with, we are using the simplest one, that is the Sky mode. This is going to generate a pop-up window which asks for the description. Let it be a default value. Next, we are going to upload the program which we want to simulate using this particular simulation. And I'm going to select temperature-collect.c, which is one of the sample program. We have two other options. One is the clean and the compile. Clean here refers to deleting all of the binary files which are being generated from the previous compilation. Direct compilation results in compilation of the previously compiled file, and the new features which we are added to the new saved program does not get compiled. So it's always better to clean and then to compile every time. Compile command. This is the default command which is used to get the compilation underway. So now clean and then compile. This might take a few minutes. Once the compilation is completed, we get a compilation completed message, and the create option gets highlighted. That's when we know that the compilation is successful. That's it. The compilation is completed and we have the create option highlighted. Let's create a simulation now. This again pop-ups a window asking for the number of nodes which needs to be deployed. Let's take it as 5. Then the positioning. The positioning has various different options. There is the random positioning, linear positioning, eclipse positioning, and the manual positioning. Position interval. These position intervals is based on your x, y, and the z coordinates, and these coordinates are helpful for the manual positioning of the nodes. So for now I'm going to select the random positioning and I'm going to add 5 modes. As stated earlier, the network window is the place where we deploy the nodes, and we have different options available so that we can add different attributes to those nodes, which can be seen through the view option. We have the LEDs for each of the nodes. We have the background grid, which is helpful for designing the x and the y coordinates for each of the nodes for manual positioning of these nodes. And then we are going to have the positions which are indicated by the x and the y axes. And then we have the radio traffic, which can be either turned on or off depending on the requirement of the simulation, and other options which are available. So in the next video we can see about the various steps involved in how to start this simulation. Thank you.
Hello everyone, this is Sinai. I'm gonna show you how to run 2 simple programs on Kuja simulator. Let's get started. We already know how to add modes to the network window. I'm gonna start the simulation now by clicking on Start button. Now the simulation has started. Here is the mode output window. This output window is a console output window where we can print the results like this. Then the timeline window, it shows the 5 different modes with different events happening. We have radio traffic, radio on or off, and LEDs. This blue line shows the blue LED is on. The red lines in between shows that red LED is on at that situation. And this black dot shows the radio events. I'll show the different tools on Kuja simulator. Let's view breakpoints. Breakpoints is to break the simulation based on certain events, like when the button is pressed, when the LEDs are on, when the output is logged, when IR is generated, when position is changed, when radio is on or off. Let us select LED. Okay, see, it is stopped. It's because red color LED is on here. When the red LED gets on, the simulation is stopped. That is, it has broken at that situation. Okay. Now the simulation script editor. This is the script editor to change the script of the simulator. Next, we have the buffer view. This is the buffer where it shows the time in milliseconds and the ID of the mode and the write or read access where ID is performing, and the byte array where the message is stored in hexadecimal, and the source. Then the next tool is mode radio duty cycle. This is the duty cycle. It shows the CPU percentage used by each mode and the average percent of CPU used. When you pass, you get passed. Stop. It's working. Then mode information. You can view the information of each mode by clicking on the mode ID here. Let's select one now. By clicking on mode type information, you get the complete mode information from mode identifier, description, and the source file .c file, and the firmware .sky file, and the compile commands. Target is equal to sky. You can also view mode interface viewer. You can view the position, rhyme address, IP address, mode, cycle, clock, then mode attributes, button, ID, etc. When you click on the rhyme address, you get 1.0. Button, you get the button. This shows the different interfaces on mode. When you click on LED, the blue LED is on here. When you click on remove, the mode has gone now. It is removed. The next is the mode interface we already saw just now, and Msp CLI is the command line interface, and the code watcher. In the code watcher, you can view the source code of the mode and the instructions, machine instructions which is happening, and the breakpoints. We don't have any breakpoints here. Then we have Msp Stack Watcher. Msp Stack Watcher, you can identify the stack push and pops here. See, at this point the maximum push and pop is happening. You can also monitor stack overflows by clicking this button. We have Msp Cycle Watcher, where we have cycle counter and reset the count. And next we have collect view. Collect view. These are the bytes transferred. This is the data collect window, where you can view different sensor data collected over light, temperature, humidity, battery, the power consumption, duty cycle, also the sensor mapping, node control, etc. This is the simple program in Kuja simulator. Next, I'm going to show you client server program in Kuja simulation. File, new simulation, remove, create modes, add mode, create mode, use timer here, browse. My file is at Contiki examples, IPv6, then RPL UDP. First I'm gonna select UDP server, open, compile. Okay, it's done now. Create. I'll add 2 servers. Okay, 1 and 2. We drag it here. Then we're gonna add clients. We select sky mode, browse, UDP client.c, open, compile, create. We can add 3 clients, add modes. Okay, I'm gonna start the simulation now. Start. We can see the different events happening here and the mode output. Yeah, the mode with ID 2 is a server. You can see the UDP server started here. The mode with ID 4, 5 and 3 are the client modes, and the mode with ID 1 is a server mode, and this is the port 8765/5678, local or remote port where the client and server are connected. Here is the data. Now the ID 5, which is a client, sending data hello 1. ID 4 is also a client sending data hello 1. ID 2 is a server. It is receiving data from the client number 4. Like that. Now tools, serial socket. This shows the number of bytes of data transferred from server or client. We are currently viewing the server. Okay. We can change the settings here. We can add external tool paths here. And we are using the external tools like Z1 or Kuja modes, etc. We can add the Kuja extensions here. can move up or move down or remove the extension like that. You can also set the buffer size. The log output message size is currently 4000 bytes. You can also change it or set to default. Okay, finally we are done with Kuja simulation. We already know that Kuja has many advantages, like it is open source, it has simple UI, flexible, efficient and scalable. It uses basic C, C++ codes. It supports multiple platforms like Z1, SkyMote, etc. It has native TCP or IP support. It supports fully standardized IPv6 and v4. It supports low power standards like 6LoWPAN, RPL, COAP, etc. Thank you. Thank you for watching. Please do like and share.